In economics, or in game theory in particular, the term Homo economicus is often modeled through the assumption of perfect rationality. That is the so-called economic man, the entity that makes rational and narrowly self-interested decisions. The reality and the evidence shows that is not the case. And here is a perfect example. Here's an article from the fashion industry in which this brand, Burberry, burned something around $36.5 million of unsold clothes last year. And the question remains, how come they produce so much? How come they couldn't properly forecast that expected demand? This module is about that, is demand forecasting. And what you will learn is the following. Number one, how to appreciate the need for forecasting, why that is important for business. Number two, how to apply the right forecast technique to different scenarios. So we have many tools at our disposal, but how can we select the right one, the suitable one? Number three, how to assess a forecast accuracy by using a tool called mean absolute deviation, or MAD. So we want to measure how wrong or the level of error in our prediction so that we can learn and improve. And we're going to do that by means of this tool. So let us start. What is a forecast? A forecast is a prediction of the future events used for planning purposes. Okay, so everybody has a plan until they get hit in the face. That is a famous statement from Mike Tyson, the boxer. And I think this man can testify about that. The man who was supposed to become a king. And I hope you can still recognize this individual. That's Prince Charles. And he can testify that predicting the future is hard. And just to show you how hard it is, Paul Krugman is a Nobel Prize in economics. And when he talked about the internet many years ago, he said that by the year 2005 or so, it will become clear that the internet's impact on the economy has been no greater than the fax machine. And he based his statement on the so-called Metcalfe's law, which you can of course read on your own time just for fun. But we all know now in 2020, he was very, very wrong about that. Okay, so when we're talking about forecast, we are talking about different type of forecast. Of course, we are talking about economic forecast. These are the ones that address business cycles, inflation rates, money supply, and so on. And we know that usually they're very wrong. We also have technological forecast. So we're predicting the rate of technological progress. And here we have futurist, whose name is Alvin Toffler. He just passed away some years ago, but he released several books. He's an author, and he could predict a lot of the things that are happening now. So this is about technological forecast. It's about extrapolating current technologies into the future. Finally, we have demand forecast, which is about predicting sales of existing products and services. And that is our business today with this module. It's about demand forecast. Okay, so first of all, we have to understand that demand forecast is not a formula. It's actually a process. And in this process, that is we can call it the forecasting system, many inputs are needed. First, we need to decide what is the appropriate forecasting model or technique we're going to use. Number two, we want to incorporate some kind of historical data, some trends, some behaviors, some cycles from the past, because who knows, this can be emulated for the future. And we might want to include other type of relevant factors, like a virus, a pandemic, or something that is happening in the environment that might play a significant role. Now, with regards to the forecasting model, which is the scope for this particular module, there is an additional input, and these are the so-called parameters, Because just like with the radio, and you can tune the radio so that you can get the right signal, here is the same. We want to tune that particular technique, that formula, by means of variables so that it can create what we expect. You see? So we put everything into this black box of the forecasting system, and we have an output. And it could be like a document. This symbol represents a report or a document. And this could be an initial draft of the sales forecast. But that is just a draft, because we still need to adjust further on, maybe by some kind of subjective inputs and views, additional information, vision, strategies of the company, so that we can create our final forecast. And this final forecast has many users. We are talking about finance, human resources, marketing, operations, supply chain managers, and so on. And the question is, why? And the answer is because if we know what we can expect with regards to our sales, we can make decisions such as what is the necessary manpower that we need to have, what is the necessary install capacity that we need to have, what is the necessary resources in general that we need to have in order to make that happen. Okay, so selecting the more suitable forecasting model involve different decisions or considerations. For example, number one, the amount and type of available data. Do we have historical data, sales from the past? Maybe yes, maybe not. We don't have anything. Maybe we just have anecdotal data. What is the degree of accuracy that we need? Because if we really want to be very precise, we will need more data. We need to incorporate more quantitative and qualitative data to our system. We also need to think about the length of forecast horizon. Are we forecasting for the next week, for the next month, or for the next year, or even next 10 years from now? Because depending on this length, we might lean more into a qualitative or a quantitative or a mixture of both approaches. And then if we have data, do we have patterns, behaviors? Does the data shows a trend, a cycle, a seasonality? We need to assess that, because we can argue that the same, ceteris paribus, as they say in economics, all variables remaining the same, we can emulate that pattern towards the future. So here's a list of considerations in order to select the right tool. Remember, the formula that I'm going to show you are tools. Okay, so we have on the left qualitative methods, on the right quantitative methods. So what is the difference? Qualitative methods, we like to use them for long-term periods of time. So qualitative means voice of experts. So people get together, they discuss, and they can forecast what is going to happen based on their expertise, based on their knowledge. It's used when situation is vague and little data exists, such as new products. For example, the iPad. When Apple decided to launch the iPad, there was nothing like that before. In fact, when that product was launched, people were mocking about it. They were laughing. They say that it's like a big phone in which you couldn't make phone calls, right? So it was a new product. Same with new technologies. So it's very vague. It's hard to predict. That means it involves intuition and experience. Perhaps that is one of the skills that Mr. Steve Jobs was having. He had that intuition. He was not really a scientist. He was not Einstein, as people sometimes compare him with. He was very, very intuitive. Okay, so that is qualitative approach. Then we have, of course, the quantitative. This is hard data, and we use it for short-term periods of time. We're talking about days, months, quarters, maybe a year can be included. It's used when the situation is stable and historical data exists. So that means that you have the product already exists or similar products exist, same with technologies. It involves a lot of mathematical techniques. So for example, forecasting the sales of color televisions, iPads, phones, etc. And lastly, assumes that what has occurred in the past will continue to occur in the future, which is a hard bet if you think about it, because what is it, 2 months ago? So we are in a moment of crisis because of a virus, and 3 months ago nobody was thinking about this, that it was going to be like it is now. So there is this assumption that things will remain the same and will continue the same. Okay, so demand, historical demand data might show different patterns. For example, we might have a horizontal pattern. That means data cluster, that means cluster moves about a horizontal line. Here's a horizontal line. What kind of products do you think falls into this category? Well, here's an example. Toilet paper. Toilet paper is very stable demand. It's actually linked to the population growth of a community, city, or country, so to say. So it's a very stable, predictable type of demand, unless an unusual event like a virus, a pandemic event happens. Then you have erratic demand, which, well, you know the story. Second, we have trends. Sometimes products become very trendy, they say. So demand is going up, 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 maybe to a certain point, and then it will stop. Like in mathematics, they call it the asymptote. So it will stop at a certain point. So what kind of product can you think? Here's one. I think it's called beard straighten. It makes your beard straight. Okay, so I don't have a beard, so I'm not so 100% sure how it works, but I suppose that if you look like this and you use this comb, kind of electric comb, then you will look like this gentleman here. Even the eyebrows and hair looks different. Maybe he's using the same tool. So this product nowadays it is very trendy because using beards is also very trendy. Now we also have seasonalities, like ice creams. You know, here comes the summer, it's hot, ice creams go up. Maybe in the winter, other type of products will be more common. So this is no big thing. And then we have another pattern which is called cyclical. So a cycle. It resembles seasonalities, except that the timeline, if you have a closer look, is way more extended. Whereas here you have months, here you have years, like economic cycles. But you also have in business a lot of products that behave like that, or services, such as tourism. So whenever the economy is in healthy, in a good condition, people travel a lot. But in the moment is the opposite case, a crisis, economic crisis occurs, then people stop traveling. That is quite obvious. So these are just examples from the different patterns. And depending on the industry that your product belongs, you might get an insight of which patterns are the ones governing that industry. But you might also want to dive into the historical data and see how this product has been behaving. Maybe it's a very successful product. Maybe you have the nicest toilet paper in the market, and it's not behaving like horizontal, it's behaving more like a trend. Everybody wants to have your toilet paper. It could be the case. So when you think about products, then you have to think about which kind of demand patterns could this have. For example, a post-massage gun. I don't know if you know this. A post-massage gun, what do you think? Horizontal, trend, seasonality, or cycle? What about smartwatches? Is that something trendy? Yes? No? How about athleisure, which is a mixture of athletics and leisure? That is the fashion that is integrating elements of sports into casual wear, such as maybe what you're wearing at this moment. Maybe you're wearing something like these leggings, which initially were intended for running, I guess, and now you can just go to school with that. Or you can go to school like this gentleman here. He looks like he's going to jump from an airplane, from a parachute. So you see, this is a trend. So companies like Adidas, Nike, they know Puma, they know this athleisure trend very well. And here we have another one, a pet bed. So what is it with this product? Do you think it's a trendy horizontal seasonality? So we can discuss all about that. You can share these thoughts with me if you want on our MS Teams post. Okay, so with regards to seasonality patterns, it is important to recognize the following. Seasonalities can be not just broken in the form of months, but we can also think about other time periods. We can also think about weeks, in which every period is a day, is the length of a day, and we have 7 seasons. We can also think about a period of months, and we can break them in weeks. So we can have 4 or 4.5 seasons, or we can also break the period of month in days, and then we can talk about 28 to 31 or even 30, just to make things simpler. And then of course years, and years can be broken into quarters, like in business in the US, companies give reports in quarters. So you have 4 months or even weeks, 52 weeks. So this is going to become relevant because whenever you're applying forecasting techniques for seasonality, some of these techniques involve the variable of seasons. So you need to integrate these numbers that you see here into that formula. So at this point, what matters is that you recognize the meaning of seasons for seasonality type of data. By the way, that is a seasonality product, Bosch Garden Tools. So let us start with our collection of forecasting techniques. The one that is here is very, very sophisticated. It is actually called naive forecast. And this is how it works. It assumes that the demand in the next period is the same as the demand in most recent periods. So for example, if January sales were 68, then February sales will be 68. So maybe you take now your calculators, because you might need to calculate this. So this is how it might look. So this is January. These are the number of orders you received. And in January, you made a forecast. And what is going to be the forecast based on naive forecast? Is going to be exactly the same as the number of real actual orders you received in January. So the next month tries to replicate that month that you just experienced. February comes. Surprise, surprise. Remember that you forecasted 120? Well, guess what? It didn't happen. You only managed to sell 90 orders this month. All right, we learned that. So now for the forecast for the next time period, we are going to emulate, and it's going to become 90. And then comes reality. And these are the actual sales, the actual orders. In this case, 100. And we use this 100 again for the next period. And then comes reality, and so on. And this is how it works. Now, you might say, well, what kind of forecast is this? It's always wrong. Well, I told you so. Forecasts are always wrong. But the question is, how wrong is wrong? You see? And don't underestimate naive forecast, because this, first of all, is very cost effective. I mean, I think you can even manage to do it even without a calculator. And it's very efficient. And it can be a good starting point, because when you really have no clue about what you will expect for the future, why not starting with a naive forecast and get a feeling of how demand is behaving, constructing data, so that the next period of time, now you have some kind of learning, and then you can apply a more complex and elegant type of forecast. You can actually apply 2 different types of forecasts at the same time, or even 3, and always compare them all. So naive forecast actually can be used as a benchmark, because picture this, wouldn't it be ironic that you use a very sophisticated forecast that even includes the weather forecast, because who knows, when it's cold and rainy, people buy more. This is something that Amazon, by the way, has learned. So you incorporate that forecast and maybe it works fine, but who knows, maybe the naive forecast is even better when you measure its accuracy. Now we have another one called the simple moving average. And there is a reason why it's called like that, and I hope you will understand by the end of this slide. So, simple moving average is using the average demand for a fixed sequence of periods. So in other words, it relies on historical data, otherwise you cannot perform it, and then you define the number of periods you want to take into account. If we're talking about months, do you want to take into account 2 months? Do you want to take into account 5, 6 months, 10, 20? You can, as long as you have data, you have full freedom. But be aware of the following. By manipulating that so-called smoothing parameter, that n, that number of periods, this will create an effect on your forecast. Why is that? Because the longer you go back in history, the more data from the old times you're incorporating in order to calculate the new future. Yeah? Okay, so you will see this with an example in a minute. This technique, simple moving average, is suited for stable demand with no pronounced behavioral pattern. That means no trends. You can have some fluctuations and the forecast can cope with that. But in the moment you have a sharp trend, this technique, simple moving average, cannot follow up this trend, cannot grow in the same rate as the trend. And the reason is simple. The reason it has to do with the fact that it's an average. And if you take a lot of historical data, a lot of periods from the past, and these are, let's say, on a very low level of sales, well, you're going to end up with an average which is something not so dramatically high as the trend is suggesting. Okay, so now I'm trying to explain here something that in mathematics you will see it right away. We have a formula. The formula is quite simple. I mean, you can have a look, maybe you can deduct how it works, but it's as simple as adding up, that's a sum, the number of periods we want to include, 3 months, 6 months, 10 months, and just divide everything by that same number of periods. So let me show you how it works with an example. Okay, so let us apply this technique called simple moving average, and we're going to apply it on a period of 3 months. Once again, please keep in mind, it's not that it's always 3 months. We can go as any period we want. This is just an example for 3 months. So we have our data, we have our sales per month, and we're going to calculate, in this case, April, because remember, this is a 3-month simple moving average, so we require historical data for at least 3 months. So if we want to calculate the orders for November, which we have no clue because we are in October, the way we're going to calculate is by the formula, which is 90. So let me go here, 90 plus 110 plus 130. And we divide everything by the number of periods we took, which is 3. And that's what you see here. That means the forecast for November is going to be 110. Yeah? Here's another one. So how did we calculate this 103 for April? Well, we took 120 plus 90 plus 100 divided by 3. And that's the forecast. How do we calculate the 88? Well, now we move just 3 months. Remember, it's a 3-month simple moving average. So we take 90 plus 100 plus 75 divided by 3, and we get this number. What about the 95? Well, now we go here, 100 plus 75 plus 110 divided by 3, that equals 95. And please, I hope you understand how the rest are calculated. So in real life, you might want to use an Excel to do this. You put the formula and then you scroll down the formula and everything gets calculated. Very simple. This is a 3-month simple moving average. Now, we are going to perform the same technique, but have a look. It's a 5-month simple moving average. Hence, the reason why we have no forecast here, because we need to have 5 data points that we're going to sum and make an average so that we can calculate the forecast. So for the case of November, which is the example that we have here, we do it like this. The last 5 data points are 90 plus 110 plus 130 plus 75 plus 50 divided by 5 equals 91. Maybe here there is an interesting remark. You do realize that although October is the most recent data point and September is the following least recent and 130 even less, and this is just becoming older data, we are giving them the same weight, the same level of importance, because at the end we just add them up. We just add them all up equally and divide it by 5. It doesn't have to be like that. We can also give weights. So think about 100%, and from that 100%, you might say, well, the 90, because it's the most recent data point from the history, let's give it a higher importance. So maybe it's 30% of that 100. And that will be the following, maybe 20. And then we keep going to the history until we complete 100, but every time with less weight. This is the weighted moving average approach. Okay, so let's make a quick comparison. Here we have a chart with orders and the timeline. And these are our actual sales that were performed through the time. You can see it in the blue line. These are the ones we just calculated. You can see clearly that's the 5-month moving average. Hence, you don't have data or forecast for 5 months because you needed to collect that data in order to start. And that will be the 3-month. And what is it that you see here? Compare the performance of each of these forecasts with the performance of the actual sales. You notice first that there is a little bit of a delay effect, as if this point goes down and this point goes down, and then sales go up, sales go up, sales go down, sales go down. And the same happens on the 5-month average. But when we compare these two, we can say that the 5-month simple moving average is a little bit more smooth. It's more flat, right? Have a look at the line. Look how it looks. Look how it fluctuates. Even though the demand is fluctuating like crazy, the forecast is very stable. So the larger we go with the number of periods, the more of that effect you're going to get. That is the so-called smoothing effect. And if you go to the opposite, the least number of periods you take, then you will have a more kind of responsive type of forecast, as we can see here. Which forecast is the best? Well, it depends. It depends on what? It depends on the level of error that is giving you. And how do you measure error? Well, by the difference of actual data, actual sales, and what you forecasted. So there is no simple answer to that question. It depends at the end on the level of error. That is always the answer. So you want to make the accuracy and determine which parameter is suitable for your particular needs. Okay, so now we go into an extension of the simple moving average, and that is the one that I already gave you a teaser. It's called the weighted moving average. So in the past, all data points were equally weighted. Now we're going to distinguish that. So weights are assigned to the most recent data. So we give more importance to the most recent data and least importance to the old data. That is the logic. It is used when some trends might be present. Older data usually is less important. So we don't want to have the old data contaminating, so to say, that new fresh forecast. We only want to take into account the most recent data, because if we notice that the sales are going up, this effect is the one that we want to capture. We don't want to have it contaminated with old data, okay? Weights are based on experience and intuition. Yeah. So I think I heard once a teacher of mine saying forecasting is like, it's a little bit like art. So although it's very quantitative and statistically based, there is a lot of intuition and gut feeling, you see? Nobody knows the future. So, but you can learn lessons from your errors, which by the way, you can precisely measure, and then start tweaking always your techniques. So the whole idea is to minimize, to minimize error through the periods of time, as every year your forecasts are becoming more and more precise, more sophisticated perhaps. It considers more inputs. Okay, so adjust moving average method to more closely reflect data fluctuations. Okay, this is done by the weights. And we have here a formula, and the formula is basically, now we have a new element, which is the weighting factor. And the whole idea is to allocate different levels of weights to our data points. But please remember, the highest level, the highest weight goes to the most recent data. Again, the highest weight goes to the most recent data. Sometimes I've seen people doing exactly the opposite, and it makes no sense at all. Okay, so here we have again an example. So we have the month of August, September, and October, and we have 3 data points. And let's say that this is our number of orders. And here we have a weight allocation. In this particular example, the author decided to give October half of the weight, 50%, 33, September, and lastly 17. Yeah. So the way you apply this is by simply multiplying the demand, the data point, by its weight. So that is October, that will be September, and that will be August. And this is how you calculate it. Yeah. You might also find in some other, in literature in general, that sometimes everything is divided by the number, the total number of the weights. Since these were percentages, it is as if we are dividing by 1. But some people like to do things more complex, and instead of allocating percentages, they just give numbers. Okay, you can also do that, but you just have to divide everything by the total of numbers, so that at the end you can get these percentages. So once again, most recent data, highest weight, oldest data, the lowest weight, and the weights are usually given to you, but in real life, in the business world, it could be that you have to decide these weights. Here is another method, and now it has a very elegant kind of name. The name is called Exponential Smoothing. And don't get intimidated by these names. There are reasons why they're called like that. And you might remember the exponential function, how it looks like in mathematics, right? So you remember a graph of exponential function, how it looks? Well, so this formula that you see here, this method, recreates that. So it's still an averaging method, just like the ones I showed you before. Just like the simple moving average or the weighted moving average, this is still an averaging method. It also weights the most recent data more strongly. But here is why it's called exponential, because it weights, the weights decline exponentially. So the formula, you don't have to worry about allocating weights. The formula does it alone. So what the formula is doing is that it's allocating importance, weights, every time less and less. And if you create a chart, a graph of this, it will resemble an exponential function. So it goes exponentially. It's not linear, it's exponentially. Now, this is an interesting approach because it reacts more to recent changes. It's widely used, it's very accurate. It involves little record keeping for past data. This is a very important sentence. It means you don't really need to have historical data. It means you can start from scratch, and then you build your forecast, and then little by little, you know, the formula starts recreating, let's say, starts functioning. You will see how it works once I apply this formula. I'm just going to read it. Well, F stands for, guess what? Forecast. T is time. That's the period of time. It could be a day, a month, a year, a quarter. It depends what you're forecasting. And because we are today on T, tomorrow or the next month will be T plus 1. So the forecast for the next period. Then we have an alpha here and here. The alpha is the so-called weighting factor or smoothing constant. This is a smoothing parameter. It's a parameter you play with. It can also have many different values. Just like going back to the previous methods, the letter N, which was used for number of periods, the W, which was used for the weights, for weighted moving average. Now we have an alpha, and these are parameters. D stands for the current demand, that's why it's DT, plus 1 minus alpha, so it's the opposite of the complement of alpha, times multiplied by the forecast that was done for today, for this period. Okay, so let me show you how it works. So once again, we have our data set. As you can see, all the periods of time from January to December. And we have demand. And let's say that we don't have all this data suddenly. It's like this is building up through the time. Okay, so we're going to calculate February. Now, this is where the artistic part of the forecasting happens. And I'm going to show you why. So we're going to forecast. And we're going to use an alpha of 0.30. This is just given to us. In real life, sometimes companies have this as a policy. Okay, so 0.30 times the demand of the period 1. What was the real demand? 37. Okay, 37. Plus 1 minus alpha. And here, this is the artistic part of this forecasting. We are supposed to use the forecast, the intended forecast for January. But guess what? We are in January. Nobody made any kind of forecast at all because this is the starting point. You see? We have no forecast. It is in this moment, and this is a pure convention, that we are going to use as a forecast the demand. That's why we have 37. Again, just for this period, for the beginning, we are going to use, because we have no forecast, this forecast is going to be the same as the real demand. That's why we have a 37. And the result is going to be 37 for obvious reasons. Okay, it's fine. It's always like this in the beginning. But then you are going to see what happens afterwards. Then we go to the next period. Okay, we stick to the alpha of 30. The real demand, the actual sales for the second period was 40. This is the actual sales. And this is this 40. 1 minus alpha, that is a 0.7. And what was the number that we forecasted for February? 37. All right, here goes the 37 now. And now you see, we have a difference now. So now the engine of this forecast is starting to gain momentum. So the forecast for the third period is 37.9. And we just keep it like that. We just call it forecast 3. And we will use this number later on, because when we continue, we are going to reach to the level of having demand 54. And it was the forecast that was calculated for December, which we don't have here, you have to do it on your own, was 50.84. And then we obtain the forecast for the next period, that would be the next year, the next January. Okay, so now we are going to contrast the two values of alphas, the 0.3 and the 0.5. So if you perform the same exercise that I just described on your own, or why not, you can also use Excel, you're going to end up with these figures. So these are the ones that we just previously calculated, but we can also use a different alpha. So what do you think? What can you deduct? And then you will say, well, it's a bit difficult to tell you just by looking at raw data. So that's why we rely on charts, and now it becomes more visible. So Once again, in blue, we have the actual sales. And look how they fluctuate, how they behave. You also notice an upward trend. Do you see that? It's going from this level and it finishes in this level. So it's going more or less very kind of stable going up. And these two lines are our calculations by using different forecasts. And what is it that you notice? Have a look at the alpha 30, how it looks like. Very flat, no? And alpha 0.5, it looks a little bit less. It's a little bit more sensible, more sensitive to the changes in the actual demand, as you can see here. So for example, this upward trend, it is manifested here with the 0.50, and look how it looks with the alpha of 0.30. So once again, you have a parameter that recreates a level of, that creates a smoothing effect. Okay. What else can we conclude? Well, we can say that both work very good with following the trend. Regardless the level of smoothness or fluctuations, they both follow the trend. This is something that you wouldn't get if you can run the exercise on your own with a simple moving average, for example. It cannot follow up this upward trend. Okay, so what can we deduct out of these alphas? Okay, so here we have a nice comparative table. Here we have large alpha values. This could be 0. Not just 5, 0.7, 0.8, and small alphas. So if we go for a high value of alpha, the consideration of past values is weak. Yeah, that's why it fluctuates the most, because it considers the most recent data, and therefore if the recent data fluctuates, it will fluctuate. Here you have the opposite case. It considers a lot of the past values, is very strong, and because it considers a lot of the past values, this creates the smoothing effect. Yeah. So the opposite, consideration of recent values, here is strong, that will be weak. Smoothing of time series is weak. Remember the graph 0.5, how it fluctuated. If you go higher, it's even weaker because it considers strongly the recent values. And here you have, of course, the opposite effect. Is very smooth. So the adaptation to the new demand level is fast. It's very sensitive to changes in demand. And this one is more like a laggard. It has a delayed effect and it's not so dramatic. It's more cool, more smooth. So small alphas is more flat, in colloquial words, and large will be more reactive and responsive. So this is just a nice summary so that you can compare these two. All right, so the next technique that I have for you is a trend line analysis, such as a linear regression analysis. The previous techniques that we have seen before, they belong to the family, the so-called family of time series. So we have a sequence of data equidistant, and then we emulate the future based on the past. This one here belongs to the family of causality as cause and effect. It means that the result of one variable depends on the value of another variable. The result of y depends on the value of x. So depending on the value of x, you have a y. I hope you got me, you understood what I tried to say. So the idea is fitting a trend line to historical data points to project it into the medium to long range. Linear trends can be found using the method called the least squares technique, which is, this method is about minimizing the sum of the squared errors or deviations. Here's an example or a visualization. Suppose that your data points, your historical data, are represented by these black dots. So what we're going to recreate is a line that resembles the behavior of the dots. Of course, not so perfectly, as you can see. It resembles a trend, but of course, you always have some errors or some deviations. These are the deviations that it is being discussed, and we want to position this line in a way that minimizes these distances. It's the best fit line. And if you remember your mathematics, this line looks like this. That is a linear regression equation. Remember? Maybe you have seen it with different letters. Maybe, for instance, in my case, I remember the slope, the variable or letter that we used for the slope was an m. But it doesn't matter. It is exactly the same. Now, that means that in order to identify a value of y, and that will be the forecast that we're calculating, we need a value of x. So this could be, for example, give me the money invested in advertising or promoting an article, and this could be the sales. So the more we promote it, the more sales we can obtain. So we can always predict a level of sales based on how much money we are investing in promotion. You see this relationship between x and y? Okay. Then we have to, in order to create this equation, we have to solve a and b, and we always start with b, because b, that's the formula for b. Once we calculate b, we can later use b for calculating a, sorry. So that is the reason why we start with b. Now, don't get intimidated once again with these Greek letters and formulas. They are just very time consuming, but they are very simple to do it. Very simple. It's just about summing up the multiplication of x and y minus n is the number of periods that we have of data points. And then that is an average. This x bar is the average of all the x values, the average of all the y values, the sum of all the x values to the square. So we just made it all to the square and add everything up, minus periods, time, the average of all the x square values. So it's simple, but time consuming. Once we solve b, we can solve a. And once again, that is an y bar, that's an average, that is an x bar, that is an average. And once we have a and b, well, we have our equation. So, for instance, if we have data, and this is given to us completely, like this could be last year's sales from January till December, and we have a total of sales, so that will be the total sum of x, and this is y, and these are the sales, and the total sum of y, the sigma y will be 557. In order to construct b on a, well, we need to calculate x times y, x times y, x times y, and that will be the sum of x times y. And we also need to calculate x to the square. Where is our x? Here. 1 to the square, 1. 2 times 2, 4. 3 times 3, 9. Even my daughter, she's 8 years old, can do this all the way. Maybe here not. Maybe she will need a calculator. Otherwise, she's a genius if she can do this, and I just don't know that she is. And here is the sum of all the x square. Okay? And this is our raw materials. That's why we're doing this, for executing the formulas. And these are our formulas. So x bar, well, is the sum of all the x divided by 12. The sum of all the y's divided by 12, because we have 12 periods. That is the letter n. And then we have this very large, intimidating formula, remember? Now it doesn't look so intimidating because we have done our homework and we have calculated all these numbers. So maybe we can go back a little bit, just that you remember. See? That is x, y, and we just add them all up, sorry, and that is 3,867 going forward. That is here, because that's this formula. Minus, how many periods do we have? 12. What was the x bar value? 6.5. What is the x bar value? 46.42. Where is this 650 coming from? Well, that is the sum of all the x to the square. You forgot that? Let's go back. It's here. This is our column of x to the square, and that will be the sum. And that's here. And so on. And then you just need a calculator, or maybe you can do it in your head. Who knows? And then you should reach to this value. And eventually, we're going to have our linear equation, and it's going to look like this. So for any given value of x, we can calculate a value of y. For example, if this is our linear trend line, and we want to forecast period 13, and x means the number of periods, we just plug that into the formula and we get that value. So once again, this is our real data through the year. It actually has an upward trend, and here that will be our result, and it's actually very precise. It's actually almost hitting this reality. But you notice we're always moving back and forth. We can always predict. This is no longer time series. We can say for any given number, we can calculate its respective value. That's how it functions. So that is a linear regression. It helped by means of least squares method. Okay, so this is how we can use it for forecasting. Finally, the last method that I have to show you, we have seen methods for horizontal trends. We have seen methods for horizontal trends with a little bit of upward trend, and we have seen with real upward trend as well, and we have seen methods that can cope with that. Weighted moving average, exponential smoothing, for instance. We have seen causal methods like the linear regression that I just showed you. Now this is for seasonalities. This is when we have our pattern. Remember the patterns of seasonality, and we're going to use a method called multiplicative seasonal model. And multiplicative seasonal model can adjust train data for seasonal variations in demand, and we have many products. Could be water skis, snow motorcycles. I don't know what would be the right name for these vehicles. They could be manufactured at the same plant. It's just that depending on the seasonality, they will start producing this during the winter and maybe this during the summer, so that they are ready on the market on time. Bush garden tools, another seasonality product. So there are many seasonality products, and I'm going to teach you how it works by means of an example. And this example, we want to forecast 2020, and all we know, and maybe this information is given to us by the marketing department, is that we expect a certain number of units to be sold, but we don't know how these units are distributed through the months. What we have is a historical demand, the historical data from the 3 last periods, 2017, 18, and 19, from January till December. A closer look might reveal that, if you see here, there is a presence of seasonality, because these numbers look larger than these numbers here. So you can say that in these months, there's a higher demand than in these months, as well as here. So we can claim there is seasonality. So the very first step, so we're going to construct a table. So here I'm going to show you data. And the whole idea is to calculate this seasonal index. That is our goal, but we have to go by parts. Okay, so let's call step number 1. That is this one. Step number 1 finds the average historical demand per season. For example, season could be a month. So what will be the average demand, the average level for demand? And then you will say, well, for January, it's going to be 90. For February, 80, which is just the average. Always the average. You see? The average per season. Because the second step is to make what they call an X double bar, or a grand mean, or in colloquial terms, the average of the averages. Now that will be, if these are our averages per season, now we can make an average of everything. And that will be this 94. And we need this because now we're going to compare these two columns. That's the reason why we need to have them in this way. Okay, so average per season, complete average of everything, all the data sets. We want to do that because we want to calculate a seasonal index. So that is going to function as our benchmark. Okay, so this is how it works. The seasonal index for January is the 90 divided by 94. So that will be 0.957. The next will be 80 divided by 94, 85 by 94, and so on. What is it that you notice here with the values? You might say, well, some values are below 1, and some values, like these ones here, are above 1. Okay? That means these are going to be the valleys of the seasonality, and these are going to be the peaks of the seasonality. Because the way we're going to use this seasonal index, we're going to apply this to the expected demand of 2020. Remember? I hope you still remember that figure. It was expected 1,200 units in total. But that is in total. What we need to do is, we need to calculate an average per month or a monthly level of sales, and we just do it by dividing by the number of periods. In this case, we have 12 periods because we went for months. If that would be quarters, then it would be divided by 4 because of the number of periods. Okay? And then we simply multiply by its respective index. So we divide it, we have an average per month, and then we multiply by its index, and now we have January 2020. And now we have February 2020. That is the seasonality index for February. And we have to do the same for the rest of the year. So eventually, we're going to end up with this data. Now I just went directly to the visualization. And you can see these three thin lines. These are our historical data. And the big red line is the forecast. And you can see how the forecast resembles the pattern, the seasonality pattern from the past. And it's also a little bit higher because they were expecting a total of 1,200 units. I can assume that at least it's a higher annual demand as 2017 and 2018. Maybe in comparison with 2019, it's kind of, there was no real growth. It's kind of the same, but this is just the forecast. And this is how you calculate a forecast whenever you have seasonality patterns on your data set. Okay, so that is the last method. So the way to measure the accuracy or precision of our forecast is by means of measuring error. And error in the concept of forecast means the difference between the actual sales and the figure that you have forecasted for that same time period. And this metric can come in different forms. It can be measured in units. It can also be measured in percentage. And there is a collection of metrics, the ones that you see here, so that just for your awareness. But we are going to focus only in one of those, which is among the most popular. And I'm talking about mean absolute deviation, or MAD. And the equation, it looks like the following. It's the sum of the difference, the absolute difference. That is the reason of these parallel lines, because we don't care if the difference is positive or if that difference is negative. We only care about the magnitude of the difference. You see? And we divide this sum by the number of periods. N, it stands for the total number of periods. So this is how it works. Suppose you have 12 periods. This could be a year. You have already the history of your sales. You also have the figures that you have forecasted in that previous year. And these are the ones you get to see here. So now we're going to calculate the error, the deviation, and we are going to start here. Why in the second period? Because remember, that is smoothing exponential smoothing. So we kind of recreated the first forecast very artistically. This is basically the same as the demand. So we have to omit that. Otherwise, it means that we were 100% precise, you know, when we execute the difference between this and that. So we just omit that. That will add noise to our calculation. But from here onwards, now we can measure. Period 2, the difference between 40 and 37, that is 3. In absolute numbers, also 3. For period 3, that will be 3.10. For period 4, the difference is a minus 1.83. Minus because of the difference between 37 minus 38. But because we only care about its magnitude, we will use 1.83. That is the absolute number. This is what we care here. This is our formula. So we continue doing the same all the way until here, because this is the number we want to see. That is the sum of these magnitudes of deviations. And we divide that number by the number of periods, in this case 11, because we omitted period 1. And that is our result. The absolute deviation is 4.85 units, which is really not that bad when you think about it. We can say that we underestimated the demand by almost 5 units. Like our forecast were a bit shorter in this sense. So it doesn't matter, we only care about the deviation. So that is 4.85. Now, of course, in real life, people don't do it like this. They rely on Excel spreadsheets at the list, or even specialized packages as the ones you get to see here. You have Quattro Pro. You also have some statistical packages. Perhaps you are familiar with SPSS or Minitab. These are softwares for statistics. Or specialized forecasting packages such as Forecast Pro, Autobox, Forecast Master. These names can become familiar once you enter into the working field. All right, so just to wrap everything up, these are the module highlights. First, the 3 basic principles of forecasting are: 1, forecasts are always wrong. They are rarely perfect. Second, forecasts are more accurate for groups than individual items. This is called aggregation. We want to forecast students. We don't forecast just IM, IB students. We put them all in the same box, in the same cluster. Number 3, forecasts are more accurate in the shorter term than in the longer time horizons. I think this is quite obvious. Keep in mind, in the shorter term, we rely on quantitative statistical methods, and in the longer term, we rely more in qualitative approaches. Again, qualitative approaches, there are different methods. We haven't explored those, but it's just basically discussions and voice of experts. It's just pure gut feeling, in a way, to put it simple. The forecasting process involves 5 steps. First, decide what to forecast. Second, evaluate and analyze the right data. Select and test the model. You select based on data patterns, for instance. Do the forecast and then measure the error or the accuracy, as we have seen. Okay, so now is your time to work. And what I'm going to show you are 2 exercises. One is actually a bit long. This is time series method. So we have seen naive, moving average. In this case, you're going to apply 3 and 6 months. That is the parameter n. And then you're going to apply weighted average with a period or n of 6. And you're going to use the following weights, with the heaviest weight applied to the most recent months. Keep that in mind. You're also going to run an exponential smoothing using an alpha of 0.3. So you can do this by hand, or you can do this by Excel. If you want to, I recommend Excel because once you input the formulas, you just scroll down the formulas and voila, you have the results. But you can also practice either way. It's just that by hand is a bit more time consuming, but hey, I suppose that you have a lot of time now, isn't it? Okay, so what is the math the deviation of each of these methods. So you're going to compare the results of all these calculations versus the real actual sales. And then you're going to tell me which from all these methods, as you see here, seems to work the best. How about that? The second exercise is is based on causal approach. It's not longer time series. You're going to run a linear regression analysis. And here is your data set. So basically you have an X and you have a Y, as you can see. That will be your X, that be your Y. And here's a hint. You can also do it with Excel. You can do it by hand, it's more time consuming, and Excel. By hand involves you have to input this data in one column, this data in the other column, and then you select with your mouse, you select all these matrix. You make a right click. Yeah, and you go to the top where you can find your charts, because you're looking for a chart called the scatter plot. It's just dots. I'm going to repeat it. It's called scatter plot. You look for a scatter plot, you make the chart, and it's just a chart with dots. Once you have that chart, you touch one of the dots, and then with the right click, you open a window, and in that window you select Add Trend Line. You select Add Trend Line, another window opens, then you have to select a linear trend line, because guess what? You also have other shapes like exponential, for instance. You select linear. And you're not done yet, because right on the bottom of that window, you're going to see a message saying, hey, do you want me to display the linear equation? And then you tick that little box. You say, yes, I want that. Then that's it. You press that button, I'm done. And then magically that beautiful line will appear, and then you will get also your linear equation. Isn't that great? Thank you, Bill Gates, for this. All right. So having said that, I'm saying goodbye with this picture of the man who once upon a time thought that he was going to be a king. But hey, who am I to talk about the future? Maybe he's going to be the king. No? That could be, wouldn't that be great? I would be happy so. All right, thanks a lot and bye-bye.